It is my pleasure to introduce our speaker for today. Susanne Aalto is a professor in radio astronomy at Chalmers University of Technology in Gothenburg, Sweden. She got her PhD from Chalmers, working on molecular clouds in starburst galaxies, and was a postdoc at Stewart Observatory in Arizona and at Caltech in Pasadena, where she worked with the Owens Valley Array. Professor Aalto is a recipient of a European Research Council Advanced Grant and a prestigious Knut and Alice Wallenberg Foundation grant. She has led the Division of Astronomy and Plasma Physics in Chalmers, was elected in 2019 to the Swedish Royal Academy of Sciences, and since last year, because apparently there wasn't enough going on, she also leads the university-wide faculty senate at Chalmers. So Professor Aalto will talk today about some of her favorite galaxies, and the title is Take a Thieves, What is Hiding Inside the Most Compact and Obscure Galaxy Nuclei. So without further introduction, I would like to turn the control to Professor Aalto.
Great. Thank you so much, Alberto, for this wonderful introduction. It's great to be here. I'm going to talk today about some of the most deeply obscured objects in the universe and how we can try and find out what's hiding behind the enormous veils of dust. But before I get cracking on that, I wanted to thank, of course, the CONquest team, the team behind the CONquest survey, and the master team. And while doing so, I realized that the names of the collaborations are all about some kind of intergalactic overlordy stuff, so it's a bit embarrassing. So roughly today, we're going to start about talking about dusty nuclei, why we care about them, and how we can use molecules as tools. And then we'll have a very quick look at some of the most famous obscured nuclei in the nearby universe, NGC 1068, and then move on to the center stage here, the compact obscured nuclei, the CONs. If there's time towards the end, I hope there will be some. We'll talk a bit about some dusty feedback towards these sources. So why do we care about dusty galaxies? Well, luminous and ultraluminous infrared galaxies, ULIRGs and LIRGs, are dusty galaxies. They're often interacting, and they're fundamental to our understanding of galaxy evolution. Because in these embedded nuclei, there's a very active evolutionary stage of both star formation and of the growth of supermassive black holes. So to understand, first of all, these galaxies, their true role, of course, in the evolution of the universe, but also the nature and evolution of the activity that they're hiding is crucial to our understanding. Of course, many of these embedded nuclei in the LIRGs and ULIRGs host obscured AGNs. And most AGNs in the universe are obscured. So it's extremely important to understand, of course, the processes, the properties of this obscuring structure and how it links to the nature of the growing black hole. We also need to understand the dust-embedded activity in order to understand the starburst AGN connection, and also how the shape and structure of the torus is linked to the feeding of the black hole and its feedback. We're also trying to understand how the small scale, where we're talking about less than a parsec obscuration, that we often see in X-rays, is linked to that we see in larger scales, 10 to 100 parsecs, and sometimes also the obscuration structure of the whole galaxy. This nuclear activity will often drive mechanical feedback in the form of molecular winds, jets, and outflows, which are part of the whole process in understanding the evolution of the dusty galaxies. Now, I like to use molecules as tools, and that there are many ways to study dusty galaxies at very many wavelength regimes. But now I'm going to focus on the molecules that we study at the longer wavelengths, centimeter and millimeter wavelengths. And I'm an extragalactic astronomer, and we started off in the early days of extragalactic millimeter astronomy in using primarily CO as our tracer, carbon monoxide. It traces molecular gas of fairly low density, and to me, low density is a few hundred per cubic centimeter. And it's a very good tracer of the overall gas content and dynamics to identify clouds, for example, and study their stability. If we want to study the denser gas, then it is useful to go to molecules with, for example, higher dipole moments, like, for example, HCl and HCl+. And these are also very standard probes to study the dense gas phase, which has a gas density of 2 orders of magnitude higher, about 10 to the 4 per cubic centimeter. Now we're getting closer to the activity now. We study star formation, and we study the AGN activity, and we study the dynamics of nuclear dense gas. And we have to, of course, use these molecules as probes because the cold H2 is a silent molecule and that has no net emission. So we need these molecules as probes. And we can use various molecular tracers to really study many aspects of the star formation and AGN activity, in particular the dust-embedded one. The gas distribution and dynamics, dynamical masses, non-circular motions, out and inflows, as we're going to talk about very shortly. We can also get the physical conditions, temperature and density tracers, so we can use molecules specifically suitable to probe specific parts of the molecular ISM. We can also study, as we shall see shortly, the impact of radiative pumping on molecules, and particularly in the centers of galaxies. And this is particularly suitable to probe very dust-embedded sources. Recently, we've also seen, I would say, the explosion of the field of astrochemistry. AGNs and starburst properties can be probed using the various chemical aspects of molecules. We can study the impact on the outflows on the molecular gas properties in the outflows. We can look at the impact of dynamics on the interstellar medium or the radiation on the interstellar medium. So this is an extremely promising but very complex growing new field. We can also use molecules to study stellar enrichment, for example, using molecular isotopes like 18O, 13C, for example, to study how the stars are enriching their environments and also what types of stars that are enriching the environment. There's an ongoing effort to benchmark the key diagnostic molecular species and lines, and this is something that would be a very good topic for another talk some other time. Now, extragalactic molecules, there are a vast number of molecules detected in the interstellar medium in our own galaxy, more than, I think now more than 200. And also extragalactically, we're now definitely exceeding more than 60 molecules detected. So this is, again, as I said before, this is a field that's now growing very rapidly. So how can we then use these molecules to probe the dusty nuclei? Well, a really nice example would be NGC 1068, which is a torus of molecular gas surrounding the supermassive black hole. Now, the torus, we've sort of gone from viewing that as a thin, obscuring structure that is quite stable to a more dynamic structure than we've thought about before. It's very complex. This is a cartoon from a paper by Takuma Izumi showing what he and what their group is thinking of when they think about the torus, consisting of molecular gas, outflows, failed outflows, ionized gas coming out, excuse me, from the center, atomic gas further out, and the gas flowing back in and out in an inflow. So we have a very dynamical structure of that torus where we have simultaneous in and outflows that basically constitute dynamically the torus rather than it being a static structure. Now this torus is very well probed with molecular lines and or millimeter and submeter continuum, for example. As I said, One of the most intriguing examples of such a torus is NGC1068. And here we see several, this slide is a bit busy, but it's busy because there's so much going on in the study of the torus of NGC1068. With ALMA, observations started out with very high resolution, 0.06 arc seconds, that revealed, I think perhaps even for the first time, it imaged the molecular torus around an AGN. Finding that it had a radius of about 3.5 parsecs, was very dusty and very turbulent, and it had a fairly low mass, suggesting it was not self-gravitating. The line diagnostic line ratios of HCN80+, for example, shown large variations as we were moving towards the torus, suggesting that the diagnostic value that we have assigned to these line ratios to help us chemically identify AGNs is a bit precarious. The high resolution has shown us that we need to use these line ratio identifiers with some care. And even higher resolution observations by several different groups suggested, again, really shows the incredible complexity of this structure. It reveals apparent counter-rotation, which can be actual counter-rotation, or it is an effect of an inflow or a so-called outflowing torus. So again, it demonstrates, even though at this exquisite resolution of 1.4 parsec on linear scale, it still shows how difficult it is to really arrive at a simple picture of what's happening in this, illustrating, I think, very nicely the dynamic nature of this tori. The column density has been estimating towards the center using these observations suggests column densities of gas are very high, in excess of 10 to the 23. So it's approaching being Compton thick. And we know that in X-ray observations that these nucleus is Compton thick and has a column density approaching 10 to the 25. So the molecular observations are now getting close to the obscuring, to the structure that is obscuring the nucleus also in X-rays. So even if this is high though, it's still quite benign compared to the most extremely embedded galaxy nuclei that we've found so far. Let's see if I can, whoops. Okay, I need to go back. Here we are. And these are the compact obscure nuclei, the CONs. Now these are extreme objects. Some ULIRGs, and we're going to see roughly how many very shortly as a result of our survey, are so embedded in dust that they seem to be obscured even in X-rays. They have column densities in excess of 10 to the 25 and AVs way in excess of 1,000. We have indications they're actually quite common in luminous infrared galaxies. And it's extremely important to understand this opaque phase. What are they? That's, of course, the first question. What are they hiding? What's hiding inside the vast column densities of gas and dust? So we need to understand that in order to complete our AGN senses and to understand the growth of the nuclear stellar spheroid, and also to understand the starburst AGN connection. We also need to understand these objects locally to see how they relate to distant dust-obscured galaxies. Can we find CONs also in the distant universe? This is something that we're currently working on. Here's one example. This is IC860, and one of the things that the galaxies that host CONs have in common is that they are quite boring looking. Here's IC860 taking with a Nordic optical telescope. It's not super exciting, but when we look at it in the millimeter and also in the centimeter wavelengths, as we shall see, what we're finding is that this galaxy that appears quite unassuming in the optical and it's not doing anything apparently interesting has optically thick nuclear core, which suggests a column density in excess of 10 to the 26. Now, this is similar to what's previously been found in one ULIRG after 20 by Nick Scoville and also Kazushi Sakamoto. And Nick described this as a brick wall, and I really see what he means. These are incredible column densities. There are caveats because we are assuming, of course, standard gas to dust ratios and that nothing untoward or strange is happening. But these are extreme regions. And what happens here is that the ground state lines, I've just told you before that we use, for example, lines of HCN and H2O+ to probe the dense gas in the centers of galaxies. But the problem is that for these objects, these galaxies actually become self-absorbed, or these lines. And we cannot use them to probe into the very center of these mysterious objects. So what can we do instead? Well, we can use the fact that the molecules have vibrational ladders, or many molecules have vibrational ladders that can get excited by an embedded, buried mid-infrared radiation field, but then in turn have transitions that at longer wavelengths that allow the radiation to penetrate these vast layers of gas and dust. And one such molecule is HCN that is pumped very effectively at 14 microns. It requires a very bright mid-infrared field, temperature of at least 100 Kelvin, optically thick temperature of at least 100 Kelvin. So these lines, these are extremely good tracers of embedded, very luminous dust-embedded sources. Here's one example, IC860. Again, dull, continues to be dull looking in the optical. But when we look at it with the vibrationally excited HCN, what we're seeing is that we're getting very close to the nucleus. We cannot actually probe it with the ground state lines, but with HCN, we find the structure like this. But even towards the very, very center, even the vibrationally excited HCN line, the inner 4 parsecs, the vibrationally excited HCN is losing out because of opacity effects. The molecule is basically in complete thermal equilibrium with the dust, so we lose the emission from the molecule. But what we can say from the information we have now is that we have gas densities in excess of 10 to the 7 in the inner 5 parsecs, in a very turbulent thick disk, and the temperature exceeds 250 Kelvin, although we have to be careful of heat trapping issues. The surface brightnesses and the intensities of these lines are so high that we are left with basically 2 possible sources of the emission. One is that this is a so far undetected population of fast accreting supermassive black holes, that they're so dust embedded at this stage that they cannot be detected in X-rays. And we've tried, and we are failing. An alternative possibility is that they are compact starbursts, consisting only of massive O stars. Now we're getting so close to the nucleus now with a high resolution with ALMA that we can resolve the dynamics, and that means we can put limits on how much mass we can actually stuff in there. And it means that we need an extremely skewed initial mass function in order to make this work. Or we have a combination of both, or there's something that we are missing. The cons are extremely dynamically active. So we talked about the tori being very dynamically active structures. The cons are the same, but just much more so. They have massive inflows towards their centers. The environments are extreme, very dense gas plus very dense stellar populations. So the dynamical environment also in the center becomes extremely active. Things happen quickly, and the stars and the gas can interact on short time scales. It seems like these are disk outflow systems. It's a bit surprising. but the outflows are obscured even at far infrared wavelengths. We need to go to the longer wavelengths, at centimeter wavelengths, for example, with the VLA or the future ngVLA, to detect the outflows from these objects. The outflows are also obscuring themselves through, if we look at them in lines like CO or HCN that are very abundant, the ground state lines of HCN, we see the inflow structure, but we don't see the outflow structure, which is hidden behind the inflow structure. So these are extreme objects that require everything we can throw at them, basically. I added this little image of the methanamine, CH2NH. It's a molecule I never thought I would have to be really concerned about. But it turns out to be an extremely important molecule in the CONs. And my postdoc, Mark Gorski, just submitted a paper on describing a centimeter maser emission that we detect towards these objects in this molecule. So these are extremely interesting and very strange regions. So how common are they? How common are CONs? Well, we set out on a survey with ALMA CONquest, where we entered a deep survey of 38 nearby ULIRGs, LIRGs, and low luminosity dusty galaxies in complete volume limited samples. We looked, of course, for the main transition lines that we get for free, HCN, HCO+. And of course, the main line is, the main target was the vibrational line here. We also got HLC plus and millimeter continuum images. And you see some of these images, the quality of them, and some of the spectra here on the side. The first paper is out led by Niklas Falstad with some of the first CON statistics. So what are we finding? How common are CONs? Well, it turns out that the CON detection rate is very strongly luminosity dependent. And the detection rates in ULIRGs is as high as 38%. In LIRGs, in far infrared selected LIRGs, it is also very high at 21%. When we go below luminosities of 10 to the 11, we do not detect them anymore. The host galaxy seems to be major mergers in the ULIRGs and minor mergers, but aging minor mergers in the LIRGs. Now, these are very early days. We've just started to look at the host galaxy properties. So we still have a lot of work to investigate here. There seems to be a link between the CON galaxies and collimated dusty outflows. And there also seem to be objects where in and outflows exist simultaneously. So when we're looking at the properties of the outflows, for example, if one uses the standard tracer of outflows, which is the 119 micron OH absorption line in the far infrared. The CONs, and here we have the CONs are here right on this line, and the outflow velocities are here on the y-axis. So we see, if we look at them in the far infrared, the CONs all have inflow. They're dominated by inflow structures. But when we look at them at longer wavelengths with ALMA, with the VLA, we do detect the outflows. We do detect the fast outflows that we cannot see in the far infrared. So the outflow seems to be obscured by the dust, which also means that they're probably relatively compact. So I'm going to finish this presentation. We're looking at some of these collimated molecular structures that we see in galaxies. I'll give you a couple of examples, and then I will finish with one of my absolute favorite ones. So when we looked at these objects with, for example, here's work done with a VLA towards a CON host galaxy called Zwicky 49. This is an object that does not show any sign of an outflow in the infrared. But when we looked at the OH lines, not at 119 microns, but looking at them at centimeter wavelengths, really broad and clear line wings appeared. And since then, we have also detected this outflow in CO65 with ALMA. So a very dense, apparently collimated, but we yet don't have the resolution. We're waiting for some new data. but it appears to be quite collimated and compact, the outflow that we see here. A more spectacular example, I think, is Aalto 20. This is work by Loreto Barcos Munoz, who found a collimated molecular outflow in Aalto 20, which is a very famous ultraluminous galaxy, the most nearby ultraluminous galaxy. A very dense outflow that she discovered in HCN before it was discovered in CL. So she saw this outflow in the dense gas tracer before CL. The dust in these outflow is opaque at the base. So again, it suggests extreme conditions, not just in the core of this merger galaxy, but also, at least in the beginning of the outflow, suggesting extreme conditions. For Aalto 20, it's suggested to be driven by supernova remnants, but the jury is still out on what's driving this outflow. So how can we study what drives the CON outflows? Well, we need high resolution studies. We need to go to ALMA, VLA, EMERL, and VLBI to resolve the morphology, get the velocity and ISM structure of the dusty outflow and its launch region. We need to go to the optical high resolution telescopes to probe the hotter phase of the outflow that we're going to see further out as we move away from the most extreme obscured region. But we also need high sensitivity, and I think that was very well demonstrated by the work on Zwicky 49, that when we sat on it for a long time with the VLA, we saw the outflow very clearly. So we need these big new telescopes in order to get a complete census of these outflows in the local and the distant universe. For example, SKA, ngVLA, and also James Webb, to get the line wings and also to get the full energetics of the outflow. I also want to point out that the HCN, vibrationally excited HCN, is extremely easy to detect at centimeter wavelengths, and we've done that with the VLA. And this is something that instruments such as SK and ngVLA will do beautifully, and I think without much effort. So I'm going to close with a favorite example of the collimated outflows and what we can learn when we have really high resolution with upcoming telescopes. And this is NGC 1377. And I said before that objects such as IC860 are rather unassuming to the optical eye. Well, I think this is an even better example of that. Now, this is a flattened space orange, as one of my colleagues call it. And I think that's a good description of it. It's quite boring looking in the optical. Well, if we go deep with HSD, we do see some interesting dusty structures here. But this is the most radio quiet object in the sky. Just a small lenticular galaxy, has luminosity of a few times 10 to the 9. It has an excess far infrared emission with a Q that exceeds 3.9. So it's way off the far infrared radio correlation by factors more than 37. It also has a deep silicate absorption. So what is powering this compact infrared luminosity in this interesting object? Well, when we threw ALMA at it for the first time, this is what we found. This is quite shocking. We found a collimated molecular jet. And when I talk about a jet here, I do so even though there is no radio jet. We have tried and there's no radio jet. But the molecular gas is formed, the high velocity gas is in a jet. And we're trying to figure out why. The mass outflow rates are very high. The momentum outflow, the momentum flow rates are very high. They're too high to be starburst driven. So the outflows of this galaxy are clearly not starburst driven. So is it an AGN that's driving out it? And why is there no radio jet? Well, this is what you get when you use ALMA at the absolute highest resolution. This is now a resolution of 20 to 30 milliarcseconds, and we are looking at the spatial resolution of 2 parsecs. And what we see here is, again, is this extremely collimated structure. It's very, very clumpy and also very turbulent structure. It's unclear how it's held together, but we suspect magnetic fields are involved somehow. We also have a narrow wind surrounding it that's significantly slower, and also a broader wind that surrounds the narrow wind. The wind has not yet been detected in optical lines or in the infrared lines. So what's going on? Well, with the jet is changing direction. We suggest it maybe, at least it seems to be changing direction because we have velocity reversals along the line. And this injects turbulence into the surrounding gas. Its relation to the wind is unclear, but the wind is clearly rotating in a Keplerian fashion, which suggests that it's a magneto-centrifugal wind. We cannot resolve rotation in the jet, but evidence so far suggests that the jet is also magneto-centrifugal wind. This is a different process to what we normally find in AGNs or starburst, where we normally have a radio jet and an AGN if we have a jet that drives out the gas. The processes here seem to be completely different. The jet seems to be forming not it's not carried out by a radio jet, but the jet seems to be forming in the molecular gas and acting on the molecular gas. The evidence we have so far suggests that the black hole in the center, which we now can measure the mass of quite well, is overmassive. So what we suggest that this is that we have a feeding loop where the molecular gas is driven out in the jet by magnetocentrifugal forces, not by star formation or by actions directly out of the black hole. It returns to continue to flow into the center. The gas is stripped of its angular momentum so that gas can sink to feed the supermassive black hole. And if it's caught in a loop like this is the process that can go on for quite a long time. And finally, I just wanted to say that the molecular jet of 1377 is very different than from the jet driven outflows we see in other galaxies. Here are 3 examples, M51, 1068, and ESO 420. They all have the molecular gas lining the radio jet. It's the gas is clearly carried out or being pushed by the jet. We have no such evidence of 1377. We suggest that the process there is completely different and more linked to the growth of the supermassive black hole directly. So to conclude, we talked about some of the most, the discovery of some of the most dust-embedded regions of rapid evolution that we've seen so far in the universe. Column density of 10 to the 26 suggest obscurations that we've never seen before. And this is also probably the reason why these objects have remained unhidden until the advent of telescopes such as ALMA and the VLA. We have these compact obscured nuclei are a lot more common than we thought. The really luminous galaxies, we have fractions of up to 40%. It seems to be luminosity dependent, their existence, but we still have to investigate this with a bigger sample. What's hiding in there? We don't know. The jury's still out on whether these are extremely embedded growing supermassive black holes or if they are some kind of extreme form of star formation or both. We are also really concerned about some of the assumptions we're making on the dust to gas ratio, for example. So we still have work to do in order to figure this out. And for that, we need ALMA and also the new upcoming telescopes. These objects drive outflows, but they are different than outflows that we see normally in star formation, in star forming galaxies and AGNs. They're very dusty. They seem to be collimated. And there's some evidence now that the driving force is also different than what we've seen before. Thank you very much.
Thank you, Susanne. That was a great talk. So we already have a few questions. Let me ask one of them here. So given the high optical depth in the millimeter continuum, what do you think will be the best wavelengths for high resolution follow-up studies of CONs? It's 3 to 7 millimeters, maybe longer wavelengths at centimeter waves.
That's a great and absolutely terrifying question, Aalto. So it seems like being around, what we really need, so one of the crucial data points we had, I want to say for IC860, was the 45 gigahertz detection with the VLA, because that helped us to really be clear that we're talking about prolific dust and not anything else. So that was important. We seem to be, so moving from, I'd say maybe 20 to 80 gigahertz, that is a very good regime to be in if you want to be in sort of not be super optically thick. However, meanwhile, back at the ranch, it seems like emission is leaking out in the near infrared and mid infrared from the cores. We don't know, so we're trying to figure out how it's possible that we're not getting any X-rays, because if there were stars, we should also get X-rays from the stars, right? So we don't get X-rays from the stars, we don't get X-rays from anything. We looked with New Star, we looked with Chandra. So we don't know what's going on. There's a lot of hot gas that is also leaking out in the mid-infrared. So we have a project accepted at James Webb for 2 of these objects to try and figure that out. Of course, you can imagine it's very, very clumpy, and that you will see some lines in the mid-infrared and the near-infrared. There's also a possibility that the X-rays, for some reason, are quenched. But we don't know by what. I've been torturing some X-ray astronomers the past few weeks with this question. Is it possible to quench the X-rays? And we don't have the answer to that yet. So if anyone has any ideas, if we can do that, I'd be very interested in hearing. Sorry, Alberto, that was a long answer to your question.
Wasn't my question. It was a question from the audience. But I'll ask you one question from me, out of curiosity. What are the masses that we're talking about in these cons, in the central concentrations?
So we're talking about molecular masses so it's not huge, right? It's about 10 to the 8 in the centers of the LIRGs. And in the ULIRGs, it's an order of magnitude, at least more than that, probably more. We haven't done the modeling. But again, this is very model sensitive, and everything is optically thick, crazy optically thick, right? So we could be underestimating the masses or overestimating them. So we're not sure. So take that with a grain of salt.
Absolutely. Thank you. Okay, so let's go back to the questions from the audience. Could you comment on whether polarization observations may constrain mechanisms behind the extreme molecular jet collimation? For example, by possibly revealing magnetic field geometries.
Thank you for that absolutely wonderful question. We put in an ALMA proposal because one of our students discovered or rediscovered, because we actually found an old paper from the 80s about this as well after that we can use the vibrationally excited HCN polarization, because the expected polarization degrees in the vibrationally excited HCN is going to be very high. We're talking about at least 10%. And yes, it will help us test the notion that these are disk outflow systems. So this is going to be extremely important for that. Because if we just look at the structure of them, it's easy to believe that they are just, circular. There's this really fantastic work by Kazushi Sakamoto a few years ago, where he looked at this for up to 20. And of course, if the outflow is also very dusty, it gets very hard to figure out the correct structure of the source. And here polarization studies will be crucial.
And so just a clarification, when you talk about disk outflows, you mean there is a flattened disk and there is a polar outflow related?
Yes, yes. But there are also probably multiple outflows. IC860 that I've shown, we see that there's a radio jet coming off at an angle to the molecular outflow. That's something we also see in other cons. We also see that in ARP220. We see evidences of relic outflows with LOFAR, for example. So yes, so disk outflow systems, but very complex ones. Again, there seem to be multiple types of outflows there.
Good. So let me go to another question from the audience. Meerkat recently detected at 1.28 gigahertz a 0.42 millijansky source in the NGC 1377 nucleus with a length of 6 arc seconds elongated in PA 13 degrees. So this is not, it's a comment, not a question.
Could you repeat? I want to hear all about that. What was that? So what wavelength, can you repeat?
So 1.28 gigahertz from Meerkat.
From Meerkat, okay.
0.42 millijanskys and a length of 6 arc seconds elongated in PA 13 degrees. So I guess this is a...
Oh, that's so cool. That is so interesting. I'd love to see that. Has that been published? Can one ask? Because we're not detecting it with, well, we are detecting it in X band with the VLA, but it's very faint. It's 60 microjanskys. And we've also have some data at, or Sean Linden has some data at, I think 30 gigahertz, which is very faint. We've just detected it at 1 millimeter, but we're looking at a source that's exceedingly faint. It's a fraction of a millijansky. And here he said it was 0.42 millijanskys.
Yeah. Okay, so there is another question related to a question we asked before, but the ALMA observations of CONs remind me of pre-ALMA observations of protoplanetary disks. And we know what happened when ALMA improved the resolution by a factor of 10. HL tau is the example that comes to mind. What would you expect to see with something like the ngVLA at 3 millimeters to 1 centimeter?
Oh, that's, wow. That's a nasty question. I like it. If there are stars there, so if there's star formation, the temperatures and the structures would require them to be born. I mean, it would put limits on it. There would be the gene's length and the gene structure will be affected by this extreme environment. So we should be able to start to resolve that. If they are there, we should be able to start to resolve that. Now we need to be at sub-parsec resolution. We need to be at resolutions of about, I think, 0.4 parsecs or so in these objects in order to see that. Now, of course, so that would be really good. We would be able to know if they were star forming or not. Now, its complication is, of course, that we lose the ionized gas, right, because of the pressure. So, and the dust absorption. So we have to be careful in our interpretations. But I think just resolving the structures we expect to see there because of the gene's length is something that I would expect. With increased sensitivity, we'll be able to get many more molecules. So we will be able to constrain the properties of the gas much better. And for example, if we operate using ngVLA, we can be in regimes where we don't have the same opacity issues. So I think that will be absolutely crucial. And we're trying to do things like this now with the VLA. So Mark, for example, has a ongoing project. But we are a bit sensitivity starved, right? So bigger telescopes.
More sensitivity.
Further apart.
Good, good. I think that's an excellent rationale. I like the idea. Okay, so let me ask you a question. I'm curious because so you have this outstanding question of whether there is a massive star formation happening or the power source is an AGN or something else. So it has been proposed that you can use the radio recombination lines to try to decide how hard the radiation field is. No, so a combination of the helium radio recombination lines with the hydrogen radio recombination lines. So do you have observations, or have you tried to do observations of radio recombination lines, and what do you?
We don't see anything.
Totally opaque.
No, I don't think it's opacity. I think we have issues with, so again, with the VLA of being around 30 to 45 gigahertz, we can of course start to put constraints on the masses of the ionized gas. And they are extremely faint. There is a standard ratio, for example, between 24 microns and I think 30 gigahertz that's used for normal star formation. So the cons are not on that correlation. But the reason can simply be that we don't have much ionized gas because of the pressure. So we can have stars, but we may just lose. And I think that could be the reason why we don't see the recombination lines, that the structures are so compact from which they would come, that the ionizing photons just get absorbed so quickly close to the star or close to the black hole, I guess, that we lose it. We also have an issue that many of these lines, because of these regions are so incredibly molecule rich, many of these lines get blended with, for example, cyanoacetylene, which is a pain because it's everywhere.
Yeah,
and methanamine.
Spectral weeds, yeah, exactly. Okay, so we have a couple more talks that people are complimenting you for the talk. What is the position of the cons in the broad picture of galaxy evolution? What is the role of the cons in the broad picture of galaxy evolution? What do you think?
So this is something I'm currently discussing with Claudio Ricci, who's been is putting out a paper now on the CTAGNs and a link to the merging process. So possibly, let me say that this is extreme. What I'm going to say now is just something we're talking about, right? It could be wrong. But there is a hint that the CON process happens earlier in the merging stage, so that it happens before. So it's a precursor maybe of the CTAGN process. Whether that means that they are hiding CTAGNs of growing black holes, or whether we actually have growing stars that will become revealed later on, is not clear. So I don't have the answer to that question yet, but they seem to be more common in the local universe than we thought before. So what appears to be something that happens along the way to something else. That, of course, can be said of many things. Sorry, guys. I suspect that they are growing black holes, and that it's something that happens before we see them as CTAGNs, in which case the black holes are in heightened accretion state longer than we would have thought before. So we're devising various observational methods to try and detect them at the higher redshift in the universe. It's very challenging, in particular if you want to go outside the regime of the lens sources.
Okay, we have another question here. Thank you for the talk. So this is a question about the clarification. In NGC 1377, the velocity field in the bipolar flow seems to change in the northern part from blue shifted to red shifted. Is this correct? Is there any possible explanation for this velocity behavior? So I guess this is going back to the geometry.
Yeah, thank you for the question. It's something that we really had to rack our brains about when we first saw it. The first thought we had was that we had an inclined, we were seeing somehow the edges or the inner parts of an inclined cone. But that doesn't work also now that we know that this is the orientation of the galaxy. So it's either because the outflow is, the jet is precessing, or there are two jets. And right now we're looking at new data. I just got new band 9 data.
Wow.
I'm tingly all over. So what we're seeing also, we also have other band 9 data. So we have CO625, 3 to 2, 2 to 1, 1 to 0, which is really useful. As you know, well, Alberto, having multiple lines is what you need. And we also have 13CL. So what we're seeing is that the first part of the outflow is not seen in 13CO at all, but it's only seen in CO625. So we have a massive excitation gradient of optically thin emission in the beginning that later on the gas somehow collects more into clouds or self-gravitating clouds, it appears. But there's, in 13CO, part of these velocity shift vanishes. Either, you know, because we just have a very highly excited part of the flow in the beginning, and then further out the gas settles, or we are really looking at two different flows. We're trying to figure that one out.
That's very
both are, yeah, because then you have to have, if you really have two collimated structures with opposite directions, it would be very hard to do that without having two black holes in there.
Yeah, that would be another possibility.
But you know, I put that in the sort of line of wild speculation. It's fun to be there sometimes, but one has to be careful.
Apparently, black holes merge, so it may not be that well. But okay, so let's ask the last couple of questions here. So let me go to this one. In 1377, what is the total infrared radio continuum to radio continuum luminosity? Or what would set a limit to the accretion rate, in other words?
So we use the mid-infrared emission actually to put a limit to the accretion rate, and it's not particularly high. So assuming that all the mid-infrared is coming from black hole accretion, which may or may not be true, then the accretion rate would be 1 to 2% right now. So it's not radio mode, but it's also not really into the quasar mode. And the question is, so if we believe that these outflow has been carried not by a magnetocentrifugal structure, but powered by some other way, by an outflow, then I think that one has to be powering down now. That could be what we're saying. We could see the end of an outburst that the structure is the witness of. So we don't know that. But it's sort of like, meh.
And you're not concerned about the opacity at mid-infrared wavelengths? I
am, yes. So, you know, I'm concerned about many things, Alberto. That's definitely one of them.
This could be a lower limit to the accretion rate.
Yeah. So the thing is that 1377 is a con by our standard, just barely, despite the fact that it's so low luminosity. But if it has an opaque millimeter source, it's very tiny. The upper size limit on that one is, I think by now, the last numbers we did was 0.2 parsecs. So we could have an opacity issue there, but it's going to be very hard to hide massive amounts of luminosity, I think.
Okay, very good. So let me ask the last question here. And let me rephrase it slightly. So the observations of the type that the EHT took with M87, or that observation itself from the EHT on M87, do that provide interesting data for this type of research? Yes, because it gives us information on the spin, for example. This is something we haven't thought about as of yet. In driving our outflows, for example, but that is, of course, first of all, I think just the mere amazing coolness of it, just how it blows my mind, just looking at this picture, I think is extremely important for all of us as scientists. Like this, I think it's amazing because it's something that we don't have an experience of as humans, right? We see light and we see things like, but this we have no experience of, and we still manage to get a picture of it. So whatever goes on in the world, this gives me hope for humanity. So it makes me very happy. As a scientist, I also think that the results are extremely interesting, again, because we see some interesting results on, for example, the spin of the black holes, which is useful for all of us who work with galaxy nuclei. Great. Thank you, Susanne. This has been great.